Math 2414, volume, shells. Shell method, example 4. You knew at some point we were going to revolve around something besides the x-axis or the y-axis. We're going to revolve this one around the vertical line x equals 2 and find the volume of that solid. Our lamina is the portion of the first quadrant that is bounded above by y equals x minus x squared and bounded below by the x-axis. Now before we go any further, we should probably figure out the x-intercepts because this is probably going to be our interval of integration. Finding the x-intercepts is easy because on the x-axis y is equal to 0, so we simply have to put x minus x squared is equal to 0, factor out an x, that would leave 1 minus x, and then set each factor equal to 0. Putting x equals to 0 ends that. Putting 1 minus x equal to 0 and solving it gives x equals 1. So our lamina doesn't stay up here too long. All right, if we're going to do the, well, we would have to decide shell versus washer. Excuse me, I keep saying that. That was correct. We have to decide between shell versus disc/washer. And that decision is made based on whether we want to cut this parallel to the axis of rotation or perpendicular to the axis of rotation. I would not recommend cutting this perpendicular to the axis of rotation because if you did, it would be a dy integral because the skinny side of the cut is in the y direction. And if we do that, then it needs to be a dy integral, which means we need this equation as a function of y, which means we needed to say x equals. And although it's not impossible to solve this for x, use the quadratic formula, the thing that we get would not be very pretty to integrate. So if you are a function of x, let's just put it this way. If you are a function of x, you probably want to pick a vertical cut because a vertical cut will be a dx integral and your function is already a function of x. If your equation was a function of y, so it said x equals stuff with y, it would be easier to integrate dy, which means we would need a skinny y side, which means we would need to cut it horizontally. So maybe your decision about cutting shouldn't be made based on whether it's parallel or perpendicular to the axis of rotation, but rather it should be made based on whether or not the equations that define your lamina's boundaries are functions of x or functions of y. If they are functions of x, you want your cut to have a skinny x side, you want a vertical cut. If it's a function of y, you want your cut to have a skinny y side, it would be a horizontal cut. Since this is a function of x, I want my cut to have a skinny x side so that we do a dx integral. I'm cutting this vertically. So again, maybe the decision on how to cut it should be based on whether it's a function of x, vertical cut, or function of y, horizontal cut. Then you can say, all right, my cut is parallel to my axis of rotation, therefore I'm going to do the shell method. And remember, the shell method is the integral, this will be a dx integral because the skinny side is x, of 2 pi radius height. And we know what our limits of integration are. They're from 0 to 1, but my spidey senses are tingling and making me think, should this go from 1 to 0? At the end, we'll know. The harder part, though, is locating the radius and the height. Well, the height's not too bad. If we pick some random x value here to cut, our height is going to be this distance. But that's just the y-coordinate there. But at that point on the graph, y is equal to x minus x squared. So that's what our that's what our height is going to be. This y-coordinate, but based on this x, that y-coordinate would be x minus x squared. So hooray for that, that wasn't too bad. But what about the radius? Let's get this set up. Radius, height was x minus x squared. Well, what about our radius? Where is our radius? radius is the distance between the axis of rotation and the cut. But relative to where I cut it, what is that radius? Is it x? No. X is right here. This measures the distance from the origin. So what's the radius? Well, what happens if we add the x plus the radius? The x plus the radius will always take us from 0 to 2, and that distance is 2. And that means that our radius, if we solve for it, is 2 minus x. It's all about putting what you know with what you want and seeing how they're related. In this case, they add up to 2. Solve for the radius, we get 2 minus x, and now we finally got the integral set up. I don't think I've said it lately, but the hardest part about these problems are the setups. All right, let's play this out. Well, how are we going to integrate this product? Answer, we don't. Kill the product by foiling it out, and then integrate that. And while we're at it, let's pull out the 2 pi. All right. 2 times x is 2x, I'm doing FOIL. 2 times negative x squared is negative 2x squared. Inside, negative x times x is negative x squared. Last, negative x times negative x squared is positive x cubed. Okay. I can combine those like terms, but I think I won't. I'm ready to integrate. The antiderivative of 2x is x squared. The antiderivative of 2x squared is 2/3 x cubed. Or minus 2x squared is minus 2/3 x cubed. The antiderivative of minus x squared is minus 1/3 x cubed. All right, I see the advantage to combining them. The fractions wouldn't be there. But plus the antiderivative of x cubed is 1/4 x to the 4th. And this is going from 0 to 1. 0 does, the lower limit does make the antiderivative 0, so we can ignore that. At some point that won't happen. But waiting for it to happen, and that hasn't happened yet. When I substitute 1, that will be easy. I get 2 pi times 1 squared is 1, minus 2/3, minus 1/3, plus 1/4. 1 and 0 are best numbers to put in. Well, negative 2/3 and negative 1/3 is negative 1, which will cancel the positive 1 and leave a 1/4. So we get 2 pi times 1/4, which is 2 pi over 4, which reduces to pi over 2. And that's the volume. Yeah, shell method. Shell method is a good plan of attack when your cut is parallel to the axis of rotation. I think I'm going to make one more short video just to summarize the plans of attack for both the disc and washer method and the shell method to help you decide how do I start a problem.